Now, let's have a closer look at the formal definition or the formal problem. Yeah, we'd like to formalize everything a little bit. So let's have a look at the formal problem. Yeah, we looked at what actually do we want to achieve, and now let's try to formalize that a little bit so that we know what we're talking about. And then we have again an overview of things that are actually out there before we dig into the details. Yeah, so here is the problem definition. So we have as an input the vector space that we're working on, yeah, consisting of d dimensions. That is a feature vector space of n dimensions. Sorry, not d dimensions, n dimensions. Yeah, so the features are d1 to dn, and what we want to have is a minimal subspace over these prime dimensions, which is a subset of d. Which is optimal for a given data mining task. Yeah? So minimality increases the efficiency, so minimal subspace minimality increases the efficiency, reduces the effects of the cursive dimensionality, and of course also increases interpretability. Yeah? So that is the motivation. And the challenge is obviously that optimality, of course, so because we want to be optimal for a given data mining task, so optimality obviously depends on what kind of task do we apply. Yeah? What kind of task do we want to solve? Yeah? So that is the first challenge. So optimality is application specific. The second challenge is that, well, if we have n features, there are 2 to the power O of 2 to the power, actually, because it's 2 to the power of n minus 1 possible subspaces M, which is just all combinations of subsets of these d1 to dn, which is 2 to the power of n minus 1 actually. Yeah? So the search space is very, very similar to the search space of frequent item set of the frequent item set mining problem, if you recall that, where we want to count how many count the frequency of values that are now features and value combinations, so combinations of features. Yeah, and the search space is also 2 to the power of n, of course. N is in that case the number of items that are possible. Yeah? So the search space is more or less the same. The problem here is now that typically we don't have some monotonicity criterion on the quality of subspaces. We have that in the frequent item set mining problem, because the frequency of items sets is monotonic. But here it's not the case typically. Yeah? So and this monotonicity criterion allows us in the frequent item set mining problem to apply some kind of efficient search strategy, like the a priori algorithm and stuff like that. And at least especially we know when to stop the search. Yeah, but that is not the case here in the problem of feature selection. And we have to keep that in mind. Yeah, and features might only be useful in combination with other features. We just talked about that. There's this information here. So just looking at individual features might be a little bit not enough actually, because we may have several features that are irrelevant for themselves, but the combination makes a perfect relevant projection, so to say. Yeah. Okay, yeah, for many popular criteria, feature selection is an exponential problem because of this search space here. Yeah, so that's why most algorithms actually employ some search heuristics for this optimal, minimal optimal subspace that we want to find. Yeah, that is what we want to find, a minimal subspace which is optimal for a given task. And since all the possible subspaces we would have to examine in an exhaustive search is 2 to the power of n, so we need to employ some search heuristics. Yeah, so that is the basic idea. And now typically we have two main components when we talk about feature selection. So the first step is that we need to think about how to generate feature subsets, how to generate those subspaces that that are candidates for the optimal one. Yeah, the optimal one is minimal and optimal for a given task, and we probably have to. I mean, we could try to pick by chance the best one, but of course we want to search for that for this perfect subspace M. Yeah, so one task is in the whole thing is how to actually generate candidates for the optimal one. Yeah. So we could look at single dimensions, and of course we should look at combinations of dimensions of single dimensions, which are subsets in that case. So that is the candidate generation, and then of course we have to evaluate the candidate, yeah, because we want not some subspace, but we want the minimal that is optimal for a given task. Yeah, so we have to evaluate those candidates that we generate in the first step, and that is the second step: feature subset evaluation, candidate subset or subspace evaluation. And here we typically have some kind of performance scores like information gain, chi-square, entropy, and stuff like that. Or we could try to evaluate the subset in the context of the performance of the learning algorithm, because that is everything here, which is done here, is pre-processing, of course, and we want to apply some learning algorithm afterwards. And of course, the performance of the learning algorithm that we apply afterwards could also be an evaluation criterion for this subset generation. Yeah? And we actually will discuss these two questions in reverse order. So we will start with feature subset generation. So how can we actually get with a suitable algorithm in less than 2 to the power of n times, so to say, or O of 2 to the power of n complexity, some candidates that are really good candidates actually. Yeah? In the best case, the optimal solution will be among the candidates that we generate here in the first step. Yeah? But we will start here in the reverse order. Once again, we'll start here with measures how we can evaluate the candidates actually. Yeah? So how to select and evaluate the features that we get. And the second question that we take care of is the first one here, is how to traverse the search space. And before we do that, we'll have a look at different methods on how to evaluate features and subsets of features, which are subspaces. And there are basically 3 methods out there. The first one is our filter methods. They explore the general characteristics of the data independent of some learning algorithm. Yeah? So chi-square statistics, entropy, and stuff like that. Yeah? So they are somehow model agnostic. Yeah? We don't care about what is actually employed afterwards, so we can just apply them in the general case, so to say. The second one are so-called wrapper methods. So the learning algorithm is used for the evaluation of the subspace. So we come up with a subspace, apply the learning, and then see what's actually happening. Yeah? And if the learning accuracy is good, or whatever target we have, or whatever target function we have is good, then we would keep that subspace. If not, then we try another one. And third is the so-called embedded methods, where the feature selection is part of the learning algorithm. Yeah, so that is, for example, done in all the clustering stuff we will talk about in a couple of weeks. Yeah, when we talk about clustering high-dimensional data, most of those methods are actually embedded methods. So the feature selection part is somehow integrated into the learning algorithm. Yeah, and of course we'll have a short, closer look at all those 3 different things here.